So we're going to take a look at something that sounds kind of scary, and that's mutarotation. So mutarotation happens in sugars. So when you eat a sugar or a carbohydrate, these molecules are mutarotating in your body. Doesn't that make you feel uncomfortable and uneasy? It does me. So what does this mutarotation mean? Is it something that I need to look out for? Is it something that's healthy? Is it something that's going to hurt me? And the answer is no. It's perfectly safe. All of these sugars are doing this when they're in solution. So as soon as you put them in water or in some type of solvent, these sugars begin to mutarotate on you. So we got to figure out what that actually is consisting of, what is that term being used for. And if we go back and we take a look at the structure, we said that we can have a straight chain sugar, and I'm just going to draw it like this, or this straight chain sugar can basically give us a ring with an OH that points down, or a ring with an OH that points up. And the actual truth of the story is that what really happens with these sugars is that the ring will form and you will make one anomer. However, this ring will open back up, and the ring will open back up and then it will close back down on itself. Think of Pac-Man, right? You see this kind of circular thing blobbing through that game, and it's chomping, 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 chomping. The same thing is happening to these sugar rings. What's happening is that they have Pac-Man mouths. So the mouth will open up, and then this gives that anomeric carbon enough time to basically take that OH group and flip it. And then the ring closes back down on itself. And it does this over and over and over and over. And we actually see some equilibria that begins to form here. So the open structure, when it goes in solution, will close in on itself and form this ring. The ring will open back up, flip its OH group around, and maybe close back down on itself and lock it in a new position. That ring is then going to open back up, flip the OH around maybe, and then close back down, and maybe that OH group is in another new position. So this alpha and beta anomer is at constant war with each other all of the time, and we see this equilibrium begin to get established. Okay, well, that's what mutarotation means. It's basically a slow change in optical rotation due to the alpha and beta anomers. Okay, so what we're basically saying is that the stereochemistry is very important. And muta basically means mutate, and mutate, of course, is something changing. So we get the alpha and the beta form that constantly change back and forth, and the carbon is rotating that OH group around. Sometimes it's below the ring and sometimes it's above the ring. However, we're looking at stereochemistry here. So that means that it's not uncommon for a sugar to be placed in a polarimeter, and this polarimeter, of course, measures optical activity. And if we place that sugar in a polarimeter, in the beginning it will give us an optical rotation. So let's say that the optical rotation here that we did, as soon as we made that sugar solution, the optical rotation, let's say, was 108 degrees. What will happen, though, is that this molecule will constantly open and close the ring, back and forth, back and forth, back and forth, back and forth. The OH groups twist and turn every time it does it. And then eventually what we will get to is equilibrium, meaning the rate at which the ring is opening to give us an alpha form is the rate at which it's opening to give us a beta form, and vice versa. Or I should be saying closed. The ring closes to give us an alpha, the ring closes to give us a beta, and that equilibrium is not changing anymore. Everything's kind of come to par and to terms with itself. So what we begin to see is that in the beginning, we could have an optical rotation of, let's say, 108, and over a course of time, that optical rotation will change. And let's say that optical rotation goes to plus 43 now instead of plus 108. That is something that we can measure over the course of time, and we can actually use this polarimeter read as a measure of the kinetics of the carbohydrates. How fast is it coming to equilibrium? How fast is it twisting and turning to basically give us these anomers that need to come to terms with themselves and not change their concentration anymore? The same thing can happen on the other end too. Sometimes sugars will give us negative angles, negative reads on the polarimeter, right? So sometimes these optical rotations maybe could be, let's say, negative 73. Well, this negative 73 could go maybe to negative 12. Who knows? Or it could go to negative 147. We just simply don't know depending on the sugar. So we would put the sugar into the polarimeter and we would measure it over a course of time. And that, ladies and gentlemen, is what we call mutarotation. So there's kind of a trick here. One of your labs concerns measuring a sugar and measuring that sugar and putting it into a polarimeter. What you will find out is that if you go to the Merck, you will see the optical rotation given in ranges, and that's why they do that. So the optical rotation is always a range most of the time when it concerns a sugar. Some sugars do not open and close. We'll see some of those. Some of them do not open and close as much. However, many of them, most of them, if they're a simple sugar, if it's a monosaccharide, they do open and close quite a bit. And with those, you will see a great window there that the Merck will provide you as far as the optical rotation and how is it concerned. So the optical rotation will be a range. The problem is that it really depends on when you make the sample and when you run the sample. So if you make the sample immediately and you run the sample immediately, what you will find out is that you will get the higher or the upper ends of the window. So typically you will see the extremities. If you allow equilibrium to happen and you wait for a couple of hours before you run the sugar, you will see a much lower optical rotation most of the time. Not every single time, but most of the time it does settle back down. These numbers do get a little lower for you, and that's because the alpha and the beta anomers are both there, and they're kind of canceling each other's optical activity out. So you don't get a large of a optical activity as you would as if you immediately made it. So in the lab handout that you will have two columns of optical activity. One column will be freshly prepared, immediately ran, and the other column will be prepared and ran 24 hours after you've made that solution. That's typically what they do in industry and in a laboratory. Most of the time these sugars have been in solution for quite some time. They are not freshly prepared for you. So they go into solution, they have this solution of sugar that they are using. This is a sugar solution that's been around for a couple of hours or days maybe, and these sugar solutions, they have honed in on what these physical properties should be a little bit better. But if you're making these sugars from scratch, the story's a little bit different. You've got to give them some equilibrium time if you're using the equilibrium physical and chemical properties from a chart. So that's why the Merck gives you a range as far as optical activity goes. It's all due to mutarotation, and that's exactly what's happening here. It's all mutarotation driven. So, Mr. Pac-Man, will open his mouth up and then close it back, and the OH group could point down or the OH group could point up, and that is changing the optical activity as that happens. So eventually it all settles down, but in the beginning you see very strange things happen with the numbers when you begin to analyze these freshly made sugar solutions. So that's the definition of mutarotation. In the next video, we'll continue on with Haworth projections, and we'll look at a 5-carbon or 5-membered ring now for a sugar instead of a 6-membered ring, and see how that's a little bit different. It's not that much different, actually. If you can do a 6-membered ring, you can do a 5-membered ring without a problem. The story's the same. The OH groups are there. You still see alphas and betas. So we'll take a look at 6-membered, 5-membered rings and compare them with each other in the next video.